As you know, to meet NASA's requirements for landing on the Moon, SpaceX is developing a lunar lander version of its Starship. But there's one key piece still missing from the picture: the landing legs. And honestly, designing landing legs for something this massive is no small challenge. We're talking about a huge vehicle that has to touch down safely on an entirely different world under completely different conditions. So today, let's take a closer look at what Starship's landing legs might actually look like, and what it'll take to land this giant ship on the Moon. The good news is, SpaceX has already tested landing legs on Starship, and they've actually made them work. SN-15, Starship serial number 15, SpaceX pulled off the first fully successful high-altitude flight and landing on May 5, 2021, down at Boca Chica. It flew to about 10 kilometers, did that now famous belly flop maneuver, flipped itself upright, and came in for a smooth touchdown. After the rough endings of SN-8 through SN-11, that was a huge step forward. But even though SN-15 landed successfully, those early legs weren't really meant for anything beyond testing. They were pretty simple: 6 short, stubby legs that folded out from the base of the vehicle late in the descent, just before touchdown. It was a quick, practical design. Hinged mechanisms tucked into the skirt that swung outward and downward when needed. They were also designed to be a bit forgiving. Instead of locking instantly, the legs could adjust as they touched the ground, helping the vehicle settle more evenly on uneven terrain. Made of stainless steel to match the rest of Starship, they also included some basic shock-absorbing, crushable elements. And to be fair, they did their job. SN-15 landed upright, and the legs absorbed the impact without tipping the vehicle over. But if you look at the photos afterward, you can see they took a beating. There was visible crumpling and damage, even on what was considered a nominal landing. That's likely from sideways forces at touchdown, maybe a bit of skidding as the vehicle settled. For early prototypes, that's totally fine. These were meant to be quick, cheap, and expendable, just enough to prove the concept works. But that kind of setup isn't going to cut it for the Moon. This time, the target is the lunar South Pole, and that's a whole different challenge. The terrain out there is rough, uneven, and unpredictable, covered in sharp features, big slopes, and massive boulders that can be tens of meters across, with craters scattered all over the place. Landing there isn't just about touching down. It's about doing it safely, precisely, and without tipping over. And that's going to require something a lot more robust than those early test legs. So what will Starship's landing legs actually look like? Let's start with the version designed for the Moon, Starship Human Landing System. One important detail is that the HLS version is expected to land using high-mounted landing thrusters instead of the main engines. The goal is to avoid blasting huge amounts of lunar dust and debris across the surface. That design choice changes the entire landing dynamic and could allow for a different leg configuration than the one used on Earth landing starships. On the Moon, adjustable landing legs could be very useful. If a landing had to be aborted at the last moment and the vehicle touched down somewhere unexpected, the surface might not be perfectly flat. Whether it's the Moon or Mars, aborting late in the landing sequence may not always be possible, so the spacecraft needs to be able to deal with uneven terrain. Adjustable legs could also help if the rocket lands slightly tilted and then needs to level itself afterward. Another idea that's been suggested is a simpler mechanical system, where the legs extend downward and automatically compress depending on the force they feel when they touch the ground. In that setup, each leg would retract slightly until all of them are sharing the vehicle's weight evenly. This would naturally compensate for small differences in ground height or soil softness without requiring complicated terrain scanning systems. You can even take that idea a step further. The resistance in each leg could be calibrated based on the rocket's total mass and the number of legs supporting it. Each leg would extend until it senses its expected share of the vehicle's weight. If one leg touches the ground first because that side is higher, it compresses slightly while the other leg continues extending until they also make contact. In the end, the rocket settles into a stable position that matches the terrain beneath it. That said, the lunar version of Starship will probably land only at carefully selected sites. Before a mission, engineers will study the landing area in detail using orbital images and mapping data from missions like the NASA Artemis program. Because of that preparation, the spacecraft will either land exactly where planned or abort the attempt entirely. Still, spaceflight is all about planning for the unexpected. Engineers try to account for as many possible scenarios as they can, because when you're landing on another world, there's really no such thing as too much redundancy. Overall, the current design of the Starship human landing system will likely require very large landing legs, simply because of its height. The vehicle is extremely tall, so the legs need to extend far enough to keep the spacecraft stable on uneven lunar terrain. Because of those challenges, some people have suggested a different idea. What if you built a shorter version of Starship for the Moon? A shorter vehicle would naturally need smaller and lighter landing legs, which could simplify the design and reduce structural loads during touchdown. With a lower center of gravity, the spacecraft would also be less likely to tip over if one leg touches down slightly earlier than the others, or if the surface slope is steeper than expected. For such a tall vehicle, very large landing legs could add significant mass and complexity. They would have to absorb landing forces, deploy reliably after months in space, and deal with uneven loads on rough terrain. A shorter spacecraft might allow for simpler legs that are easier to design, test, and operate. However, redesigning Starship into a shorter lunar version would require a major engineering effort. Even though it might sound like a small change, shortening the vehicle would mean redesigning the tank structure, the engine mounting system, often called the thrust puck, the propellant plumbing, and many other internal systems. That's a lot of work, and it would take both time and money, resources that would have to come from somewhere. Since NASA largely accepted SpaceX's proposal for the Starship human landing system more or less as it was originally designed, there may not be much incentive for SpaceX to spend additional resources redesigning it. Still, it's a fascinating concept, and definitely something worth exploring further. If you're interested, we could dive deeper into that idea in another video, so feel free to leave your thoughts in the comments. Anyway, let's get back to the landing legs themselves. In the long term, the plan for lunar exploration, especially under programs like the NASA Artemis program, includes building permanent infrastructure on the Moon, such as landing pads or even launch facilities. With stable landing pads and possibly locally produced propellant in the future, large spacecraft could land much more safely without needing a completely different design. In the really long term, you could imagine something even more ambitious. A small tower with chopstick arms and a launch mount on the Moon, supplied with locally produced fuel through in situ resource utilization, ISRU. That's obviously far in the future, but it's an interesting idea to think about. If something like that were ever built, unmodified starships could potentially fly directly to the Moon and be caught or serviced there, just like on Earth. And eventually, you could imagine a similar system appearing on Mars as well, though that's likely many years, if not decades, down the road. Okay, one final question. Will Starship missions that operate only in Earth orbit ever use landing legs? The answer might actually be yes. Environmental documents from the Federal Aviation Administration suggest that SpaceX is considering another recovery option for Starship, landing offshore on autonomous drone ships. If this approach were used, Starship would likely need deployable landing legs, since the vehicle would have to stand on the platform by itself rather than being caught by the launch tower's mechanical arms. The main advantage of drone ship landings is flexibility. A floating platform can move almost anywhere in the ocean, allowing rockets to be recovered even after very high-energy missions that travel far downrange. That could be particularly useful for certain launches from NASA, military missions, or long-distance orbital trajectories where the rocket simply doesn't have enough fuel to return directly to the launch site. In those cases, having a movable landing platform dramatically increases recovery options. Another important benefit is safety and scalability. Landing far offshore reduces the risks associated with rocket landings near populated areas, including noise and the possibility of debris if something goes wrong. It also provides a backup option in case the tower catch system at the launch site is unavailable for some reason. This approach has already been proven extremely successful with Falcon 9 boosters, which have been landing on autonomous drone ships for more than a decade. Those recoveries have demonstrated that ocean-based landings can be reliable and operationally practical. However, applying the same concept to Starship would require significant modifications. The spacecraft would need landing legs integrated into its lower structure, which currently houses engines, plumbing, and other critical systems. Engineers would also need to design legs strong enough to support a vehicle that could weigh well over 100 tons during landing. In addition, SpaceX would likely need much larger drone ships than the ones currently used for Falcon 9 boosters. Starship is both heavier and larger, meaning the landing platform would have to provide greater stability and a much wider landing surface. Some proposed concepts suggest that these future platforms could approach the size of small aircraft carriers in order to safely accommodate the vehicle. There are also logistical challenges to consider. Recovering starships in distant parts of the ocean, such as the Pacific or Indian Ocean, could mean long transport times back to a launch site. In some cases, bringing the vehicle back for inspection and reuse might take weeks. To make the system practical, SpaceX might eventually need additional recovery and refurbishment facilities in other regions, possibly including locations like California or Australia. Of course, before any of this becomes reality, Starship still needs to overcome several key technical challenges. Reliable atmospheric re-entry, durable heat shield performance, and extremely precise landing control all need to be demonstrated first. Only after those milestones are achieved could drone ship landings realistically become part of regular Starship operations.